Hello everyone. In this video, I'm going to talk about the sets of numbers. First of all, I'm going to define what do we mean by a set, and then I'm going to list the sets of all numbers. So what is a set? Well, a set is simply any collection of objects. These objects could be numbers, could be letters, could be words, anything. For example, you might have something like 1, 6, 10, let's say, and 12. That is a set. Or you might have something like A, N, E, for example, and F. So that is also a set. Of course, you can add as many members as you want in the set, and these members are called elements. One more thing I want to say about the set is that it is an unordered collection of objects, so the order does not matter. In other words, I can say that this set is the same as 6, 12, 1, and 10, for example. So if you just shuffle the elements inside the set, it is not going to change. This is what I'm going to say about the sets in this video. Regarding the operations and everything else, I'm going to dedicate a special video for that, and we'll talk in more details about the set theory. Now let us come back to the sets of numbers. The first set of numbers I want to define here is the set of natural numbers. The set of natural numbers is represented by the n-like letter, and it contains all the numbers starting 1 upward. Numbers that do not have a fractional part. In other words, the so-called cardinal numbers or the counting numbers. So simply 1, 2, 3, 4, 5, etc. We call them either natural numbers or positive integers. Now, if you add 0 to this set, you'll end up with the set of whole numbers. So it is simply n with 0. So it is equal to 0, 1, 2, etc. Again, no fractional part, no negatives, only counting numbers with 0. Now let us extend this set. Let us add all the negative numbers inside the set, but again with no fractional part. So the set which contains the negatives and the positives with no fractional part and with 0 is called the set of integers. And we represent it by the Z-like letter, and this is how it looks like. Now let us add more numbers to the set. The next set I want to define here is the so-called the set of rational numbers, which is represented by the Q-like letter. Now, first of all, we need to understand what is meant by rational numbers. I will explain what a rational number is and then show you how the set Q looks like. A rational number is a number which terminates or a repeating number. What do I mean by that? Let's do some examples. For example, if you have 3.6, so this is a terminating number, 3.6, that's it. It terminates. So this is a rational number. What if I have 0.55555, etc.? That's a repeating number. It is not terminating, however, it's periodic. It is repeating, so I can write it as 0.5 bar. Or you might have something like 0.42 bar. This is also repeating. Or let's do one more example. Let's say 3.102 bar. Now, is there a more general definition of rational numbers? The answer is yes. A rational number is a number that can be expressed as a fraction p over q, where p and q are both integers. Let's come back to 3.6. Can I convert 3.6 into a fraction? Yes, I can write it as 36 over 10. So I'm able to convert 3.6 into a fraction where the denominator is 10. What if I have 6.85? That is a terminating number, and this is 685 over 100. What if I have 8.016, for example? Well, this is 8016 over 1000, and so on. So any terminating number could be expressed as a fraction where the denominator is always a power of 10. So it's either 10 or 100, which is 10 to the power of 2, or 1000, which is 10 to the power of 3, or etc. What about the repeating numbers? What about the periodic numbers? I can also convert them into a fraction, but the denominator here is either 9 or 99 or 999 and so on. So for example, 0.5 bar is 5 over 9. How many numbers do we have under the bar? We only have one number, which means we'll use 9. So this one, 0.42 bar, we have two numbers under this bar, or the cycle, in other words, contains two numbers in order to be repeated again, 42, 42, 42. This means it's 42 over 99. But there's something we need to be careful about here, is that the integral part, what I mean by the integral part, it is the part of the number before the decimal point. To the left of the decimal point, it has to be 0. Am I saying that if the integral part is not equal to 0, I'm not able to convert it into a fraction? This is not what I'm saying. So what do I do here? Well, in this case, I have to split it up into 3, like the integral part, plus 0.102 bar, the remaining part. Then I continue as usual. So in order to convert it into a fraction, I must have 0 in the integral part. So this becomes 3 plus 102 over 999. We do a common denominator and we end up with 3099. Now we can write how the set Q looks like. So the set Q is the set of all numbers of the form P over Q, where P and Q are what? Are integers, provided Q is not equal to 0 because it cannot divide by 0. So any number that can be written as P over Q, where Q is not equal to 0 and P and Q are integers, is called a rational number. Okay, what is left? So we listed the natural numbers, then we extended that to the whole numbers, then we extended this set more and obtained integers, and now we arrived at the rational numbers. So what is left? Well, the numbers that are left here are the numbers which are not terminating and not repeating at the same time, which are called irrational numbers. Let's do some examples. Let's start with the square root of 2. The square root of 2 is equal to 1.41421356 and so on. So you cannot catch a pattern. The numbers do not repeat. Whenever you cannot catch a pattern, this is an irrational number. Another example is pi. What is pi? It is 3.14159265. Again, there is no pattern here. One more example is e. What is e? It is 2.7182818, etc. Again, there is no pattern here with this number. E, by the way, is called Euler's number. So now, for the numbers that we have seen so far, they are either rational or irrational. If I combine the rationals and irrationals together, I will obtain, of course, a larger set, which is called the set of real numbers. We represent it by the R-like letter, and it is the set of all rationals and irrationals. Is that all? Well, there is one more set I want to talk about here, which is the set of complex numbers. But before that, I will define the so-called imaginary numbers. So what is an imaginary number? So an imaginary number is a number of the form a times I, where a is any real number and I is the imaginary number. It is the square root of -1, or equivalently, I squared is equal to -1. So this allows us to express any negative number in terms of I. For example, if you have -5, this can be written as 5i squared. And if you have the square root of -5, this becomes the square root of 5i squared, and this is I root 5. Now we can define the set of complex numbers. So the set of complex numbers is the set which contains the numbers of the form a plus bi, where a and b belong to R. So for example, this is a complex number, 5 plus 8i. This is another complex number, -2 plus root 7i. And a complex number consists of two parts. The first part is called the real part of the complex number, and the second part, or in other words, the number multiplied by I, is called the imaginary part of a complex number. Now finally, let me represent all the sets of numbers in a diagram. So we first start with the set of natural numbers. This is n, contains numbers 1, 2, 3, and so on. If you add 0 to the set, you will end up with the set of the whole numbers. Well, let me call it w. Now let us add the negative numbers with no fractional part. So in addition to 0, 1, 2, 3, etc., let's add etc., -3, -2, -1, and this will give us the set of integers, which is z. Now let us add all the numbers that can be expressed as a fraction, like p over q, provided q is not equal to 0 and p and q are integers. So this means we end up with the set of rational numbers that is q. Now, apart from that, are the irrational numbers. So that's a separate set. Let's put it here. So let's call it the set of irrationals. And by the way, this set is very huge. I'm just representing it like that. However, the set is very huge. It's even larger than the other set of rationals. And finally, if we combine everything, rationals and irrationals, we will end up with the set of real numbers. Now let us add the set of imaginary numbers. Finally, if we combine everything, we will end up with the set of complex numbers, which is represented by C.